Okay, welcome to section 6.4, where we're going to talk about work. Specifically, we're talking about mechanical work, which is a concept in classical mechanics, a branch of physics. And what we're going to do is we're going to introduce this concept, mechanical work done by a force, as a quantity defined by integration, because ultimately that's what it is. And so the basic formulation, if we can talk about something that's, in simplest terms with work. Imagine you have a box that's sitting on the ground, and this box has a number of forces acting on it already. So for one, its weight, or the force of gravity on the box, is a force that's acting on it. And then the ground pushes up on it so that will counteract, and this is what we call the normal force. So these are two forces that act in balance. Is a consequence of Newton's third law. Every action has an equal and opposite reaction. So while the block is being pulled down, the earth pushes up on it. But those two are balanced and so are not doing work on it because they're not moving the block. However, when you introduce another force, an external force, let's say that we're pushing it or pulling it along this the ground with a constant force F. Now, at some point, it's going to end up somewhere over here. So it will have traveled some distance. If we're measuring from the middle of the block to the new position of the middle of the block, we'll call that distance x, okay? So, as a function of distance x, what we're talking about here is work is a function of this distance and of the force. So specifically, we define here work, which is also labeled W, so ignore this part. That's confusing. Is defined as force times the distance covered. So the displacement of the box. And you'll notice that if we think about this as a function of x, it's a linear function. So if we were to graph, for instance, this function W as a function of how far we've dragged this block, then you'll see that it is actually a linear function with the slope equal to the force. So the more force you apply, the faster it moves, and the more work you've applied. All right. However, when work is done by a non-constant force, we have to change the formulation a little bit. And that's because this formulation only works when force is constant. So now we'll consider the more general formulation. By the way, what is work? Work is defined in joules, which means it is actually, we're talking about a quantity that's analogous to energy, okay? We'll talk a little bit about the units in a second. So imagine now we have some continuous force, F of x, that is also non-constant, okay? And actually, let's use a little f for that. Okay, acting on this object along the interval AB. So imagine, for instance, instead of dragging this block with a constant force, you push it for a little bit, and then you slow down, and then you push it a little bit more. So in that case, the force it'll increase and then diminish to 0, and then it'll decrease again. Then, in order to actually think about what work is, we're going to need to do the subdivision strategy that we do with integrals. And it'll be clear why in a second. So, subdivide AB into n subintervals of equal length, delta x, and in each we're going to select sample points. Then the work done in each subinterval we approximate w sub I, so meaning in each subinterval, is going to be f of x sub I star times delta x. So in other words, if we're thinking about the this block again that we're dragging, we think about dragging it just a little bit at a time. So first, we drag it a tiny force, f of x sub I star, and that will change the amount that it's traveled by delta x. And so doing each time a little bit more and a little bit more until we finally reach our destination. So we start at A and we end at B. And each time we're tugging a little bit at a time, so we can approximate this as a constant force. Okay. Then the total mechanical work done is the sum of these WIs you can see where we're going with this in the limit. So as n approaches infinity, we define mechanical work, which isn't different from the work that we were talking about, but we're formally defining it now. We're saying that in the limit, the work done on this object is the integral from a to b of f of x dx. Okay? So if we think about the consequences of what we're talking about here, at first what we said was, if we have some constant force F, then the work done actually is just the area under the curve. So if we imagine that area, and this is f of x, then that area done is the work. And we generalize this now, so as opposed to just taking the constant function and multiplying it by x, which would give us this rectangular area, what we're actually talking about then is we may have some non-constant function, like this. And so when we integrate from a to b, that'll give us the work. So all this area here then, which now we can talk about units. Force F has units of newtons, or capital N. Distance, the distance that we'll be working with here, although we will use different kinds of units, the standard units used in SI are meters, which means that work, W, has units of what we call Newton meters or joules, which we abbreviate by capital J. And joules are the standard SI unit for energy. Okay, so all that aside, let's talk about a basic example. So, basic example, we're going to talk about Hooke's law. So, imagine that you have, let's see. Imagine that you have here, along the ground, a block. And that block is attached to a wall, but it is still laying flat on the ground. And it's attached using a spring, okay? And so at its equilibrium position, okay, there's no tension on the spring. But we can tug on the spring or compress it to move the block to a different location. So here, we're stretching the spring. And you can imagine that stretching it involves adding some force. Let's call this some 2 meters away, or however long it happens to be, okay? But Hooke's law says, and this is named for a scientific revolution, natural philosopher or physicist, who discovered that this force is dependent on something called a spring constant. So every spring, depending on how stretchy it is, basically, or how easy it is to compress it, means that the force necessary to stretch this block from its equilibrium position is proportional to how far you stretch it. So this makes sense because if you have any experience working with springs, as all children at some point are, you know that to stretch a spring, the longer you stretch it, the harder it is, right? Or the more you squeeze it, the harder it gets to squeeze it. Okay? So, important pieces here, we call this the spring constant, and every spring has a spring constant that we may or may not have to determine at some point. Okay? So, all this is to say, here's our question now, or our scenario. So, a force of 10 pounds is required to hold a spring stretched 4 inches beyond its natural length. So when we say natural length, we mean beyond the equilibrium position for this spring. So question then, how much work is done in stretching it 6 inches from its natural length? All right, so how do we do this? Well, in this formulation, work has units of foot-pound. This is the imperial units version of work, okay? So if you imagine then, this means feet times pounds. And that still tracks because feet is a unit of distance, and pounds is a unit of force. Okay, so we're given some information that is going to help us determine the spring constant. So remember, what we want to know is we want to find work from an equilibrium position to a final position, the force integrated over that interval. Okay, so we do know some of this. So we know what A is. So A, that's the natural length position. So that means A is 0. So it equals 0. B, we know what B is as well. We know that we want to stretch it to 6 inches. All right. F of x, we kind of know. Oops. F of x, we know that it equals kx, but we don't know what k is yet. And that's where we need the initial information. Okay, so pre-work, and pre-work in the sense that we're doing mathematical work, not mechanical work. So if f of x equals k of x, we're given that when we stretch it 4 inches, so k times 4, then the force is 10. And we really should be careful, and we should be careful in terms of how we write our units, because we're given 10 pounds equals k times 4 inches, but we're working in foot-pounds, so inches needs to be converted to feet, okay? Which means we're actually going to write this as k times 1/3 foot, which means k is actually 30 pounds per foot. All right, so not terrible. This also does mean that we need to convert our limits of integration, because 0 is fine. 0 feet equals 0 inches. That's true. But we were given 6 inches, which is actually half a foot. Okay, so let's actually set it up now. Finally, we know that. So our work calculation is the integral from 0 to 1/2 of 30x, because 30 is k, remember? So 30 times x dx. And now this is just a standard integral that we're doing here. So we're going to take 30 x squared over 2 from 0 to 1/2. Of course, that means that's 15 times 1/2 squared. And then 0, when you plug that in, that gives you nothing. So that's fine. We'll leave it at that. And finally, this means we have 15 times 1/4. So 15 over 4 joules. Well, actually, no, not joules, sorry. Foot-pounds. And that's our answer. So in the next video, what we're going to do is we're going to extend this to other examples where we're doing work by a non-constant force. And so the important thing to keep in mind is, what's our infinitesimal slice? Yes, we're back to that concept. So the infinitesimal slice is always going to be something that looks like the force times dx. And the important thing is, what is the force on that tiny piece of whatever we're talking about? we're going to have to do some work to figure that out, right? So it looks very general. We're just talking about, oh yeah, you're adding up some tiny piece of the function times dx. But the tiny piece of the function is actually